Let's tackle this question again that's on page 23 of your further trigonometry notes. We spoke about the fact that this question has multiple methods that can be used to solve it, one of which is using a t substitution. Now, while we couldn't get it to work in class, the problem wasn't with using the t formulas, it was the representation of our final answer. So, just to remind ourselves again, using method 1, which was just making a direct substitution for an exact value of tan 30, we obtain the exact value for tan 30 from our reference sheet as 1 over root 3. And now substituting this value into the expression given, we get that 2 tan 30 degrees over 1 plus tan 30 degrees all squared is going to give us an exact value of 2 times 1 on root 3 all over 1 plus 1 on root 3 all squared. Now it's just a matter of using our fraction laws and our surd laws to simplify this fraction as much as possible. Sometimes it's easier if we write it as a division, just as opposed to working with fractions in fractions. And knowing that we can't divide by a fraction, the 1 plus 1 on 3 that comes from the original denominator, or 4 on 3, then means that we'll multiply by the reciprocal, and after cancelling any common factors, we end up with a result of 3 on 2 root 3. Now our surds work tells us that we should rationalise this denominator, so we'd multiply by root 3 on root 3, giving us a total of 3 root 3 on 2 times 3, and again having another common factor that we can cancel, leaves us with a final result of root 3 on 2. Now looking at method 2, which is the t substitution method, and knowing that we need this to get to an answer of root 3 on 2, we'll see that the t formula method is actually the much faster method in this case. So we'll start by making the statement that we'll be using the t substitution for tan theta on 2, and that gives us that theta on 2 must be equal to 30 degrees. So now we can rewrite the expression that 2 tan 30, or tan theta on 2, on 1 plus tan squared 30 is therefore equal to 2t on 1 plus t squared. And looking at the reference sheet, we can see that this is the equivalent of sine of theta. And if theta on 2 is equal to 30, then that tells us that theta itself would be double 30, which is sine of 60 degrees. Now again, using our exact ratio triangle to identify that sine of 60 is root 3 on 2, we very quickly obtain the exact answer we obtained in the previous method. The last set of examples in this section of the topic is focused on using t formulas to help us solve trigonometric equations. This is a really useful technique to turn your trigonometric equations into really basic algebraic equations that are very quickly solved. In all of these examples, we've started with an equation that is algebraic, where we're being told that t is standing for that t substitution of tan theta on 2. So if we look at question A and we begin the solving process, the equation's already factorised for us, and knowing that it equals 0, we can set both factors to 0, so t would be 0, and 2t minus 1 would be 0, giving us two solutions for t. of 0 and a half. So now by making that t substitution, that t is equal to tan on theta of 2, we're actually solving the equations for tan theta on 2 is equal to 0, and also tan theta on 2 is equal to a half. Now since half is a positive value, we are looking for an angle in the first and third quadrants, and also the exact value where the tan function is equal to 0. So looking at tan of 0 first and considering the graph, we can see that tan of 0 occurs at 0 degrees, 180 degrees, and 360 degrees. So that gives us our first set of values for theta on 2, all of them lying in the domain of 0 to 360 degrees. Tan of a half is not an exact value, but we need a value in the first and the second quadrant. So putting it into the calculator as shift tan of a half gives us out an acute angle of 26.6 degrees rounded to 1 decimal place, which means our second angle occurs at 180 plus this value, giving us a second angle of 206.6 degrees. However, since these are all values for theta on 2, we now need to solve each of these for theta by doubling all of our values. And we just need to check that everything that we end up with is then still in the same domain between 0 and 360 degrees. So doubling 0, we still get 0. Doubling 180 degrees, we get 360 degrees, so that still works, which means when we double 360 degrees to get 720, we now discount it as a value or a solution because it's now outside our given domain. The same will happen with the values found for tan of a half. So doubling the 26.6 degrees and rounding to the nearest whole number, we'll end up with 54 degrees, which is still in our domain. But the 207 degrees, which rounds to 414, is now outside of our domain, and so we'll discount it. And that gives us 3 solutions for this equation, which are 0 degrees, 54 degrees, and 360 degrees. Questions B and C follow the exact same process as question A, and their solutions are listed below, so see how you go with them and see if you can get the answers.